In this video, we go over the last section of our gas laws and talk about diffusion and effusion and Graham's law of effusion. So diffusion, as we obviously know, is moving of substances from an area of high concentration to low concentration. And effusion is going to be pretty much the same thing, except for with effusion, there is a small little opening in the partition. So diffusion is going to happen faster than effusion. It's going to take time for things to trickle out. So I always show students my diffuser in class. They think it is a smoke machine and all that, but it's really not. What it is doing is it is vaporizing our water in here and then put in some drops of essential oils, and then voila, it smells nice and fresh like peppermint or lavender, especially on test days. And anytime we have a lot of stress, there's old school diffusers where you have your reeds, but basically it is moving substances from an area of low concentration to high concentration. So our seventh gas law is Graham's law of effusion. And what it states is that if you have gases that are at the same temperature, very important that they're at the same temperature and pressure, that the rates of their effusion are going to be inversely proportional to the square roots of their molar masses. So large molecules are going to move slower, small molecules move faster. So the equation that we use looks just like this. You are going to arbitrarily, randomly assign one of the gases to be gas A and the other one to be gas B. Usually the first one in the problem is A and the second one is B. So you are comparing the rate of the effusion of gas A to the rate of effusion of gas B. So what you'll see is that that's equal to the square root of the molar mass of B over A, because this is inversely proportional. So if this is A and this is B and this is A. So if you want to do a little ABBA to remember it, you can be a dancing queen and move right along. So concept check. Let's see if we can figure this out. All right, if standing an equal distance away from ammonia and vanilla extract, okay, ammonia smells bad, and vanilla, smells good. Okay, if you are here, all right, and here is the vanilla, here is the ammonia, and they both drop, and they both are going to vaporize, okay, which one is your little nose going to smell first? Okay, well, first, NH3 is the formula for ammonia. Vanilla is C8H8O3. So, first you need to figure out the molar mass of ammonia. So the molar mass of ammonia, NH3, okay, we have one N, which is 14.01 grams per mole. We have 3 hydrogens, which is 1.008 grams per mole, for a grand total of 17.03 grams per mole for ammonia. Now, what is it going to be for vanilla? Okay, so the molar mass of C8H8O3 is going to be 8 carbons, which are going to be 12.01. We are going to have 8 hydrogens, which is 1.008 grams per mole, and 3 oxygens at 16, for a grand total of 152.14 grams per mole. So which is the bigger molecule? Which is going to be the smaller molecule? Okay, so here we see that the vanilla is going to be bigger. Okay, the ammonia is going to be smaller. So which are you going to see first or smell first? You are going to smell the ammonia first, and you are not going to be happy about it. You are going to be quite sad because it is going to smell awful. Okay, so a sample problem. Okay, compare the rate of effusion of hydrogen and oxygen at the same temperature and pressure. And again, you'll see it says same temperature and pressure. So you don't have to worry about one of them being pushed a little bit further or faster than the other. Okay, so since hydrogen came first and oxygen came second, we are going to compare the rate of hydrogen to the rate of oxygen. So we are going to take the square root of the molar mass of oxygen compared to the square root of the molar mass of hydrogen. Okay, so looking on our periodic tables, okay, the square root of the molar mass of O2 gas, oxygen is 16, so we have 2 times 16 grams per mole, which is going to give us 32. Hydrogen is 2 times 1.008 grams per mole, which is going to be 2.02. So we're going to plug in our 32 grams per mole up top and the square root of 2.02 grams per mole on the bottom. So please grab your calculators. It's important that we do these correctly. And what you need to do is first take the square root of 32, which is going to be 5.6585. And the second one is going to be the square root of 2.02, and you get 1.42. All right, you can also plug this all in at the same time in your calculator by carefully using the parentheses. You can do parentheses square root of 32 divide end parentheses divided by the square root parentheses 2.02 end parentheses, and you should get 3.98. So what does this 3.98 mean? If you have a number that is going to be greater than 1, okay, the rate of A will be faster than the rate of B by that factor. If you have a number that is less than 1, the rate of A will be slower than the rate of B by that factor. So this number is indeed greater than 1. Hydrogen, we know, is smaller than your oxygen molecule. So that means it is going to, hydrogen will effuse 3.98 times faster than oxygen gas. Okay? You can solve this problem, the exact same problem, but comparing oxygen to hydrogen, and you would get a different value. So you can compare the rate of oxygen to the rate of hydrogen the same way, but you do the molar mass of hydrogen as your numerator and the molar mass of oxygen as your denominator. And you plug in your 2.02 and your 32 here. In your calculator now, you would end up putting parentheses square root 2.02 end parentheses divided by the square root of 32 end parentheses, and what we would get now is, grab your calculator, square root 2.02 divided by the square root of 32, and you would get 0.597. So what does this number mean? Since this number is less than 1, it means that the rate of oxygen is 0.597 slower than the rate of effusion for hydrogen. Okay, so in this problem, you end up seeing that number greater than 1, 3.98, and that means that the rate of hydrogen will effuse faster than oxygen. And even if you goof and you mess up and you do the other way around, you can end up seeing that you have the correct answer, but you then have to say that you are slower in your effusion than the hydrogen. Okay, so hopefully you plug it in. I usually suggest doing the order that they give it in the problem. If not, you are okay and you'll be fine because you'll end up getting the correct answer. All right, so here you can see that this is how it's worked out in the notes, and it effuses 3.98 times faster.